Hello, everyone. Welcome to the virtual conference. I'm Yunwen Bai.
I'm Peng.
Today, Peng and I will share with you on the unified runtime service infrastructure we have been working on. In this talk, we will start from the motivation for the unified platform for VMs, containers, and bare metals, and a high-level introduction to the project Octus. Then we will dive deeper into the design and implementation details of the unified runtime project in Octus. We will finish this talk with a demo and some future works in this area. We hope you can walk away from this talk with understanding on this novel design, and even better, inspired, interested, and contribute to those projects.
Okay, let's start with background and motivation. The motivation of this work comes from the fact that we want to be able to run virtual machine and a container at the same time. Traditionally, if you want a virtual machine, you could use OpenStack. For container, you could use Kubernetes, but they're run as two different clusters. At a certain point, we have this requirement that, okay, we want to run both virtual machine and a container in the same bare metal cluster. We could still use two clusters, two different stacks. The problem with that is that it's very hard to coordinate the resource allocation between these two stacks because they're being run independently of each other. This is where the new design comes in, where we just want to have one single layer of orchestration between the workloads and the bare metal cluster. There are a few solutions to allow you to have VM pod in Kubernetes. For example, you could do the CRD and operator solution. Also, you could have some external component to Kubernetes to allow you to access the VM pod. One issue here is that by doing this, we're still going through what the Kubernetes provide us in terms of the CRI interface. And that has some limitation as to what kind of feature you can have in the virtual machine. With our project, which is called Octus, we are taking a more of a native approach, which means we are making changes to Kubernetes itself. And by doing this, we want to provide the virtual machine as a first-class citizen. And also, we want to provide the full feature for virtual machine instead of a simplified one. Here are a few challenges we're facing. First of all, we want to provide a better solution than just Kubernetes plus OpenStack. As we have discussed, we want to provide a feature like resource allocation coordination to this. Second is we want to stay open and extensible for future. If we have more workload types, we should be able to adapt to and accommodate them very easily. The third one is we will have a unified type definition for both the virtual machine and the container. What this means is that basically, a virtual machine is a first-class citizen. It's not a guest or it's not an add-on. The pod definition, for instance, is for virtual machine is very similar to the pod definition for containers. And this also leads us to the fourth challenge that we want to provide rich operations for virtual machine. Because we're a more of a native approach, we are able to extend the CRI interface. And then that allows us the possibility of providing more features there. The Octus project has a lot of features. The unified runtime is one of them. This is the focus of this talk today. But if you're interested in other part of Octus project, feel free to take a look at our virtual booth. And also, Octus project is part of a bigger project called Centaurus from us. And yeah, that will also be shown at the virtual booth. With this, I'm going to hand over to Yunwen for design and features.
Okay, let's go design. Let's first briefly give a high-level review to refresh everyone's memory before we dive into the unified runtime design. Kubelet gets container runtime endpoint via the container runtime and the container runtime endpoint command line arguments. Kubelet uses this information to construct the remote runtime services and pass it into the kube generic runtime manager object. When kube runtime manager gets the pod, it computes necessary actions, for example, create container for the given pod. With a series of API invocations, the request is then handled by the remote runtime service via the RPC call. Please keep in mind that the current only one runtime service supported in Kubernetes. Now let's take a look at the current changes in Actors. This is a high-level design diagram for the multiple runtime service management in Actors. The goals are simple. Natively support VM workload, extensible for future runtime APIs. The components highlighted in purple and tan colors are major changes to achieve these goals. The Kubelets now accept multiple runtime endpoints and actual information for the workload type and the designated runtime names. A new component, runtime registry, was added to store and maintain this information. The kubelet, when constructing the runtime manager, instead of passing in the single remote runtime service interface, now it passes in the runtime registry. The runtime registry provides getter APIs to runtime manager to get the desired workload based on the pod workload type. Each runtime service for different workload will require different spec for the workload types. The pod converter is an adapter for type conversion between actors and runtime services. In a nutshell, it translates the VM pod definition in actors to the desired spec that the remote runtime service expects. Last but not least, the runtime container interface, the runtime internal interface, and the CRR interface are extended to support VM-specific operations such as start, stop, reboot, create snapshot, etc. Now in actors, when a new pod is created and scheduled, the runtime manager gets the pod. It will call the runtime registry to get the desired runtime service for the pod based on the workload type. The desired runtime service API are called for the pod actions. We call this the pod runtime late binding. With the runtime registry, pod converter, the CRR extension, together achieve the goal to support multiple runtime services natively and make actors extensible for new runtime services and provide rich VM operations. In the next few slides, we'll share some more details of them. Let's take a closer look at the runtime service registry type and interfaces. As we can see, besides the internal API runtime services, which is constructed by Kubelet, a few more fields are maintained. The workload type is to determine which workload the runtime supports. Its primary field is used to determine the must-have runtime service on the node, which is used for node readiness check. Currently, only static registration is supported. In the future, the dynamic registration will be added. So when a node is ready to support new workload types, Kubelet won't need to be restarted to load it up. Actors is designed to support full-fledged VM definition and operations on VMs to match the feature set currently OpenStack's offer. In Actors, the CRR interface has been extended with a set of new APIs to support those operations. Need to mention that even currently, there's no deep changes at the internal data structures. With some effort to allow the runtime SDK as plugins in the remote package in Kubelet, it can be extended to support customized interfaces implementation. With multiple runtime service in Kubelet and supporting VM types, we are facing some design decisions to make. Due to the time constraint, I only share a couple here. First, we have to ensure the compute resources such as CPU, memory, etc. are controlled, shared among the VM and the container types on the node. In Octus, this is designed such a way. When the VM is created, the Octus runtime service creates the cgroup path for the VM following the same layout pattern as the container workload type. For example, it would be under kubepause, burstball / pod ID / VM ID. And the runtime service moves the VM process to the cgroup path. For VMs, there are 3 sets of metadata in terms of resource control. The first one is the cgroup metadata, which is cgroup files and each control. The second one is the runtime metadata. And the third one would be the libvirt VM domain definition. The Octus VM runtime service keeps them synchronized by checking them each time with when the VM status is reported. Another one is to handle the node status with multiple runtime service on it. Recall its primary field in the runtime registry type. In Octus, with multiple runtime service on the node, we allow the cluster admin to elect one as the primary runtime service and use it to determine the node's runtime readiness. The scheduler will only schedule the workload to the node where the desired runtime service is ready. This is very important in a cluster, so the node will be still useful as long as the primary runtime service is ready.
So with those design decisions, we are able to have this unified runtime to allow both VM and the container to run at the same time. There are a few other features that we want to mention here. One of them is the pod state management. What this allows us to do is to be able to have the VM to go from a running state to a shutdown state or to a hibernate state and come back. This is different from just shutting down and deleting a pod. This will keep all the state of the VM so that when we are ready, we can bring them back running with all the same state. In this diagram, I have a quick mechanism showing how this works. So for example, we have this VM pod running on a node. And in the definition of this pod, in the pod spec section, we have this virtual machines. And one of the key is the power spec that's showing the running state. The power spec indicates what the state the VM should be running. And now it's in the running state. So that means that the pod should be running, and it is running here. To change this, for example, at a certain point, we want to shut this down, maybe to control resource or just avoid using resources when we're not using this virtual machine. What we can do is we can issue a patch command to the pod to indicate, okay, we want to change this part to shut down. And then what that's going to do is it's going to trigger the control plan to take this pod out of resource from the node and put that in a shutdown state. When the scheduler sees this, for example, it will see the shutdown state, it will see that it's intended, so it will not try to reschedule this pod anywhere else. When we are ready to bring this back, we can do something very similar to bring it back. We can issue another patch command to change this from shutdown to running. Similarly, the control plan will see these changes, and the controller now sees that, okay, we want this to be in a running state. The controller will schedule this pod to some node. The new node can be the same node or it cannot be the same node. It all depends on the resource availability at that time. And when the pod is back up running, it will have all the state from the previous life. So it's as if we just pause the pod for some time. Here, the next one on the agenda is we were going to do a demo. So in this demo, let me switch to the demo window. In this demo, I will basically let you see, I will have two pods here. One is a virtual machine pod. As you can see, this part is the definition for the virtual machine. On the right is a traditional container pod. So you can see that it's very basic definition. It's a very simple definition. One thing I want to point out here is that, as you can see, the virtual machine now is on the same level of definition to the container. So it's not a guest, it's a first-class citizen to be there. And the rest of the definition, for example, for the resource part and the resource limited request is very similar to what the container has. Okay, so the first part of the demo is let's create these two pods. Do that. Let's create the container pod and let's create the VM pod. And here we can see that both pods are being created, and in a second we'll see that they'll go from pending to running. That's good. Now let's take a look at what the pod is actually, the VM pod. So here I'm gonna show you a few things. One is we talked about this section, right? We have this power spec to indicate what the VM should be running. And in the status section, we actually have the virtual machine status, and also we have the pod scheduled status for this pod. Okay, so that's good. Now let's try to change this to shut down and bring it back. What I'm going to do is I will issue two patches. One is to shut down the VM. That's going to work is I will do a patch like this. So if I do that, the scheduler will see that, and it will see that it's in a no schedule state, so it will not try to schedule it. If you're curious, I can show you what's in here, which is very straightforward. We just are changing the power spec section of the pod spec. Okay, and if we go back and take again look at the status, we can see that the pod is in the virtual machine shutdown state. And it's in a no schedule. No schedule means, again, the schedule will not attempt to schedule this pod when it sees that. Okay, now let's go back. Okay, now let's bring this back. How do we do that? We just do running. We'll just issue another patch to change the power spec section. And we can see that, okay, the patch has gone through. And let's just wait for it to go back to running. And now it's running. So that's very good. This demonstrates that we can have both VM and the container running at the same time, and we can have features like shutdown and the restart. That concludes the demo for today. I will hand this back to Yunwen.
Great. Thank you, Peng, for the good demo. The Octave project is still in its early stage. For the unified runtime area, there are quite few new features that have been planned. For example, the bare metal support, the GPU or device pass-through, more VM action support, integration with a storage network provider, etc. We have put some useful links here, including the Octa's project repository and some design documentation here. Feel free to browse the code, browse the design documentation, and learn more from it. The Futurewei has a virtual booth set up. Please visit us there and learn more about the project Octas and other interesting projects we are working on. Feel free to contact us if you are interested in contributing to those projects. With that, we'll be happy to take a few questions. Thank you.